Hi, welcome to Solideo Gloria Physical Chemistry lecture series. This is a section for quantum theory, so we are going to do particle in a box today. Well, you remember that we previously, in the previous lecture, we derived Schrödinger equation, especially for one dimension, by incorporating de Broglie matter wave into the classical wave equation. This is the Schrödinger equation, normal form, minus h bar square over 2m. Usually if that's a reduced mass, we use mu instead of m. Let me bring something laser pointer here. Yes. And then we have a potential and the wave function, n equals energy times wave function. This is the normal Schrödinger equation. So we kind of said there are four problems we are going to solve. The first one is the particle in a box, especially was firstly solved in one dimension. And then we'll do the rest of the other problem like rigid rotor and harmonic oscillator and hydrogen atom. This is the first problem. So particle is in a box. So in a box means that inside the box there is a particle. Outside of the box there is no particle, just like that. So we define the potential for such a box in such a way that we divide the region into three parts in a way that this is one-dimensional problem. So outside the left-hand side, region 1, right-hand side, region 3, and inside region 2. So outside of the box there is no particle. Particle cannot exist there. So potential is infinity in both sides. Region 1 and region 2, there is the potential, which is infinity. And inside of the potential, inside of the box in region 2, the potential is constant. But easily we can say the constant equals 0. Why not? So we have a potential equals 0 inside of the box. And as I said, in region 1 and region 3, 1 and 3, there is no particle. So their probability amplitude is equal to 0, which means the psi of x equals 0. And then at the boundary, meaning is that x equals 0 and x equals a. And there must be particle inside, but outside the box there is no particle, where x equals a and x equals a and x equals 0, the wave function equals 0. Okay, so psi of 0 is 0, psi of a is 0, and this is the boundary of the box, and so this is the boundary condition. In region 2, as I said, we set the potential equals 0. So this term, this is 0. So what we have here, minus h bar square over 2m d square dx square psi equals e psi. Now we multiply by minus 2m over h bar square, both sides, and gather them into one side of the equality. So what you have is d square psi dx square plus 2me over h bar square psi equals 0. So this is the differential equation, actually, second order differential equation we are going to solve. Well, this is a linear equation, so you may be familiar with that. What we have here is that something like d square plus something. In this case, 2me is rather hard to write, actually. And h bar square equals 0. So, well, with this, and we can easily obtain and easily solve this linear equation. Easily solve the equation. But we will just use our intuition to solve it in such a noticing that we make a derivative of psi twice and then have the same psi back times multiplied with a constant. If you look at that, there is such a function like making derivative twice, yielding the same function, which is a cosine or sine function. Yes, so we'll just make a general solution for that. Psi equals a cosine kx plus b sine kx. So this k is actually the k square is actually this one. So that when you make a derivative once, you have k, another time minus k. So what you're getting is minus k square is this term. So we'll put the k is square root of this. Okay, square root of this. Then that will solve this equation. Then what you're going to do is that to determine a and b. Okay, and using this boundary condition. So let's kind of have this in mind. K equals 2me square root and over h bar. Okay, then we are going to get E, energy, when you obtain K in such a way that E equals K square h bar square over 2m. Okay, so we noticed that. Right, so when we solve this, this is our solution to B, and then boundary condition psi of A and psi of 0 equals 0. So we'll substitute x equal 0 first, and then psi of 0 equals a cosine k0. Cosine k0 is cosine k0 is 1 actually. Yes, yeah, cosine 0 k0 is 0, cosine 0 is 1, so that's a plus a times 1, and sine k0 is 0, so psi of 0 is a, and then the boundary condition was that psi of 0 is 0, so a equals 0, what we have here. And then let's look at the psi of a, which is a was 0, a is 0 by this, and then b sine ka, so b sine ka, this must be 0 for the boundary condition like this. Okay, all right, so in order to b sine ka equals 0, b must not be 0, because otherwise there is no particle condition. So your sine ka is 0 when this ka term is multiple of pi, such as 0, 0 pi, 1 pi, 2 pi, 3 pi, like that. But but 0 is not allowed here, because if that's k is 0, then there, no matter what a is, that is identically 0, then, which means that means that there is no particle. So not 0, so ka equals n pi, not 0, and which means that all other natural number. Okay, so n equal 1, 2, 3, etc. Okay, so now I think we solved this problem, because we know k, which is n pi over a, and then we'll determine b with this normalization condition. By the way, at this point we know the energy. Energy was, you remember that? Shall I go back? Energy equals k square h bar square over 2m. Okay, k square h bar square over 2m, that is the energy. So energy now is indexed by this number n equal 1, 2, like that. So anyhow, energy was k square h bar square over 2m. So k square is n square pi square over a square. So a square is here, n square is here. Pi square was there, but h bar square was also multiplied here. H bar square times pi square, then, which is h bar square over 4. So, but you remember that there was a 2m in the denominator. So 2m plus 2m times 4 is 8m a square. and then n square h square. So that's energy. So energy, take this n, the number, in this case that's all natural number, we call this is a quantum number, a quantum number. So energy is now indexed by the number. I will show you how this quantization is done in the next slide. And then we have the energy, and then we are going to determine what B is. Then that will give us the final wave function. So psi n, now we index the wave function with the quantum number n, which is given here. So psi n of x equal b sine kx, and then this kx of k of this function is here a over n pi, or n pi over a. So b sine kx equal b sine n pi over a x. Okay, so this is the final form of the wave function, and now this is the probability amplitude, and then we sum up or integrate of all onto all space of the probability, which is psi star psi dx, integration done on 0 to a, where the particle exists. Okay, then this must be 1 equal 1. That is the normalization condition, meaning is that you have only one particle in the world, yes, and must have a particle in the world. Okay, and then you plug into this b sine n pi x over a, and then this is the complex, but you have a real function, which means that you have just a square of this function. So what you have is that b square, absolute value square, that's fine, integral 0 to a sine square n pi x over a dx. And this can be easily done from your calculus, of course. I could do it, but I will just skip. I will leave this to you. And then this is one, actually this integral is 0 to a, which means that a over 2. So a over 2 times b absolute value square is equal 1. Then b is 2 over a square root of 2 over a. Now we determine the constant b. Then having this into here, then psi n of x equal 2 over a of square root of 2 over a sine n pi x over a. And then the kind of region it exists as with this form is inside of the box, which is x greater than or equal to 0, less than equal to a. And then n is the number that designate the wave function. In this case, this is the quantum number. I'll show you why we call this quantum number. Next slide. Okay, so this is the energy. We are particle in a box. This is the energy, En, indexed by this n, which is here, h square n square over 8 ma square, and then psi n equals 2 over square root of 2 over a sine n pi x over a. Okay, this is the region and the quantum number. Just we had it in the just previous slide, and now it shows you the energy in terms of the index. I said index, but the quantum number. The quantum number n equal 1, which is E1 h square over 8 ma square. So it's a multiple of h square over ma square by 1. So 1 times of h square over 8 ma square. And then n equals 2, 4 times, n equals 3, 9 times of h square over 8 ma square. So energy is now here, and 4 times of that, and 3 square times of that. Okay, so energy is not continuous but quantized. or discretized, we say. Yeah. So this is the inside of the box. Outside the box, there is no particle. So wave function is 0. So inside of the box, from 0 to A, we plot the wave function itself, which is here, square root of 2 over A is the kind of maximum or minimum or maximum. And then sine n pi x over A. The largest value of x, this is the right hand side, at the end of the right hand side, which is x equal A. Then what you have is n pi at this point. Okay, so if n is 1, you have pi, n is 2, you have 2 pi, n is 3, you have 3 pi. So 2 pi is the period of the sine function, so you have just one period, half period, or 2/3 period, like that. So this is your psi 1, which is sine pi x over A. This is sine 2 pi x over A. This is sine 3 pi x over A. Okay. Now, this is the probability amplitude. Your probability is the amplitude square. So you make a square. Okay. Now what you have is that 2 over A sine square n pi x over A. Okay. So that you plotted here. Then for this one, you have just like this. You have this. For this, the green, you have two kind of half wave twice. Okay. So now I have 3, the maximum point for the n equals 3. Okay. So this is the particle in a box problem. First, to show you how the energy is quantized, because the particle is confined in the box, and you observe the quantization of energy. Okay, so let's observe or kind of draw some conclusion about the particle in one-dimensional box. So as I just mentioned, we confine the particle in a box and we observe the quantization of energy. And then what if we increase the mass of the particle and the box size, which is m, and box size A in the problem we had in our hand, we increase that, which means that we are approaching the classical mechanics. Okay. Remember that in quantum mechanics, we are dealing with microscopic object, so very light mass, like electron as such, and very tiny dimension, like couple of picometer, maybe 100 picometer, less than 100 picometer is 1 angstrom. Okay, so energy level spacing, if we increase, what I mean by increasing is mass or box size. If we increase those, energy level spacing decreases. Okay, energy level spacing, because m and a is in the denominator. Okay, and then this is the plot for n equal 20. You remember that when n equal 1, this is the sine square n pi x over A. Okay, this is the psi complex psi. Actually, it's a psi absolute value psi square. Okay, probability for n equal 1, there was just one maximum and down. N equal 2, 1 maximum, 2 maximum. Okay, n equals 3, it was 3 maximum. Okay, like this. Just to follow this, my laser pointer, not really laser pointer, but that something like that. N equal 20, you have something like 20 maximum. So n equals infinity, maybe you observe something like just a flat. Okay, so greater number of node, the higher the energy. So energy goes as a function of n square. So when you increase the energy, n increases, and then you will have that many nodes. Okay, so if you have large quantum number, meaning is that you will observe the classical behavior. We call this Bohr's correspondence principle. Okay, Bohr's correspondence principle says that with the large, big quantum number limit, we can observe the classical behavior. Okay. And now we have this wave function psi n, and then its energy. Then we know everything, or at least we can figure out all we want to know from the wave function. Okay, so firstly, we are going to calculate uncertainty in its position. So firstly, I will just explain in terms of probability. Remember that psi star psi is the probability. Psi itself is a probability amplitude. Okay, this is the probability, which is this square. So 2 over a sine square n pi x over a dx. Okay, which means that your particle is somewhere x plus x plus dx. Okay, otherwise this is the probability in this region, and otherwise 0. Meaning is that you have a particle only in the box. Okay, so now what you can do is this angle bracket inside of x, meaning is that we call this, you remember that this is called first moment of x squared, the second moment of x. Okay, so the first moment of x is actually the average value. So in order to obtain the average value, what you do is that the value times the probability and summed up in all region. Okay, that's the normal way we obtain the average value. So average is obtained x times 2 over a sine square n pi x over a dx integral 0 to a. Okay, that is the kind of limit for the box. So if you do this, what you obtain is a over 2. Yeah, this is very reasonable. You have a box size a, and then the particle go back and forth somewhere in the box. Then the average position of the particle is just exactly in the middle, which is a over 2. And now you're going to calculate x squared average, which is, well, instead of x, you put x squared here. Then you do this integration. Well, you could do it. You will do it in integration by part. Okay. Then what you obtain is this one. Now, sigma x squared, we call this a variance. Variance variance itself is actually something like in this case x. I'm sorry, this doesn't work. Okay, maybe it works. Okay, maybe it works. Okay, variance is something like x. Yeah, I gave up. Okay, so variance is something. Yeah. Let me bring. Let me clear this first. Yeah, variance is let me get the laser pointer. Variance is you can x minus x bar, x minus x average square, that is variance. Okay, so sigma x square, then that could be reduced in this form: x square average minus x average square. Okay, so x square is here and x average is here. So x average square is a square over 4. And then you do the calculation, clear this into this form. Okay, and because this is square form, so standard deviation is square root of this. So actually sigma x now without this square, a over 2 pi n, and then square root of n square pi square over 3 minus 2. Okay, so you obtain this uncertainty in position. Now we do the same thing for momentum. Now in quantum postulate 3, what you obtain, well, there is an observable. For classical observable, they correspond to a linear Hermitian operator in quantum mechanics. Okay, you have a momentum px, then the corresponding linear Hermitian operator is minus h bar ddx. Once you have an operator, then you have this so-called expectation value calculation. You have a wave function psi, and then you have a psi star, and you put your kind of sandwich, okay, sandwich between the psi star and psi, your operator, then you can obtain the expectation value. You would do the same thing for p square operator, which is p square average, okay, or expectation value. So you obtain p and p square in such a way that you have your operator, and your wave functions, and then do this integration. Okay. Of course, if you do integrate whole, you must make a derivative, meaning is you operate the operator, and do the integration. And then this is the result. For P, average is 0 because it's reasonable because in your box the particle go back and forth. So either minus direction or positive direction. Well, the average must be 0. Okay, and P square, which is not 0, and you have this number. Now you also can compute P variance, which is p square average minus p average square, which is 0. Then you have only this one. Then sigma p is square root of this, and now you have this. Okay. Now, what you obtained in the previous slide was sigma x. Now you have sigma p. So sigma x times sigma p is this. Okay. Well, this is just done in such a way. Now, the smallest value of this uncertainty in x and p at the same time, n equals 1. So what you have is pi square over 3 minus 2. Pi square, which is n is 1, n equals 1. And pi square is n, pi is that 3.14, something like that. So 3.14, something like that, square is greater than 9. 3 square, okay? So 9, well, that's the smallest estimate, okay? 9 divided by 3 is 3. 3 minus 2 is equal 1. Okay, that's smallest estimate, okay? Okay, so square root of 1 is 1. And then smallest estimate is h bar over 2. So Heisenberg's uncertainty principle says that uncertainty in conjugated variables, or a product of uncertainty of conjugated variables, is equal to or greater than h bar over 2. Well, this is the Heisenberg uncertainty principle, kind of checked in particle in a box in one dimension. Okay, so let's switch gear and explain how we may have more than 2 variable situation. Here we have S, and we just in one dimension we have just one variable. Now we have 2 variables, W and S. Okay, those are independent coordinate maybe. And then the Hamiltonian is a function of the coordinate, and first S coordinate and W coordinate. And there is no mixed term, then there is a Hamiltonian H1 of S, Hamiltonian H2 of W. Okay, then if the Hamiltonian is given as a sum of Hamiltonian 1 and Hamiltonian 2, the wave function, the total wave function, which is wave function of as a function of S and W, and then I would say the index of S degree of freedom or coordinate is m, the quantum number associated with it, and m is the quantum number associated with W. Okay, so psi nm of S and W is equal to phi n S times this is another spelling of, or the form of phi m w. Okay, which means that if your Hamiltonian is given as a sum of two Hamiltonian, then your wave function is a product of both wave functions. Okay, because you can solve separately for coordinate s in this way, coordinate w in this way. Then your energy, total energy, is a sum of energy associated with quantum number n and the energy associated with quantum number m. Meaning is that also energy of your degree of freedom of s, energy of your degree of freedom w in such a, in this notation. Okay, so when you have two or more independent coordinate or independent variable, you separate the Hamiltonian, and then separately in this way you obtain the wave function and energy, and then the total wave function is the product of those wave functions, and the total energy is the sum of the individual energy terms. Okay, so this is just, we are going to use this one to solve three-dimensional box problem. This particle now is in a three-dimensional box. Okay, just like this one. So outside of the box there is no particle, so which means that outside of the box the potential is infinity. Okay, the potential is infinity. Okay, potential is infinity. Let me just tilt a little bit. Okay, that's it. Okay, and inside of the box, the potential is kind of let's say constant, and then we just use constant equals 0. Okay, so that's about it. Okay, that's what you need. And also the wave function itself must be continuous. That's the condition for well-behaved wave function. That is a physical representation of the problem. Okay, and then we have a boundary condition at the kind of a surface. Okay, surface of the box. Okay, so this is three-dimensional problem. So what we have is that our Schrödinger equation is that minus h bar square of 2m del square psi equal E psi. This is a kind of shorthand form using the del square operator, the Laplacian operator. Laplacian is this one. So if we have this in full notation, we have this as the Schrödinger equation for particle in a three-dimensional box, and this is the kind of boundary of the box. Now we have the psi is a wave function of three coordinate x, y, and z. Now we have this partial derivative. Okay, so in order to solve this differential equation, we need to separate the variables. So psi of x and y and z is equal to x of x times y of y times z of z. Okay, but if you put this here, then first derivative operator of the Laplacian does not care functions of y and z, and only it make a derivative of x of x. Okay, then y and z functions are constant term for this operation. Likewise, for this operation, x and z component is are constant, and for this derivative of z, then x and y functions are constant for that operation, derivation. So then what you are getting, put this one over here, like here, then what you get here is this. Okay, now, well, actually x, y, z in front of d square, x of d over dx square. Now what you have done is that you divided both sides with this total wave function. Then what you're left is that 1 over x. What you're left is that 1 over y. What you're left is 1 over z. And then you have no psi or xyz in this energy side. But this energy is just a number, but you know that you separated your wave function and you could separate your Hamiltonian by Hamiltonian X, Hamiltonian Y, Hamiltonian Z, like that, then your energy is EX times plus EY plus EZ. Okay, this is the kind of easily make correspondence to each term, like EX for X term, EY for Y term, EZ for Z term. Okay, those are constants, so you can break up like that. And also your boundary condition for three-dimensional boundary condition could be reduced to, for individual X and Y and Z, into this, just the same as your one-dimensional problem. So you can solve each dimension separately, and then your final total wave function is the product of each dimension's wave function of each dimension, and your total energy is energies of each dimension. Okay, so that's the way we solve three-dimensional problem. So this is the same form as one-dimensional, of course, all three, and then you obtain x equals 2 over a square root and sine nx pi x over a. Because you this n, ny, nx, and z are all independent, so you have three indices. Now you have three coordinate and you have three indices, meaning is you have three quantum numbers, nx, ny, and g, and all quantum numbers are all natural numbers. Zero is not allowed in here. Okay, so your total wave function is the product of x of x, y of y, z of z, and then you collect all your constant, which is 8 over abc square root, and sine term of x, sine term of y, sine term of z. Okay, so this is your total wave function, and total energy is actually a square over 8m, and nx square over a square, and y square over b square, and z square over c square. Okay, this is your energy. But if you have a cubic box, meaning is that a and b and c are all the same, this could be reduced in a simple form in such a way that E equals h bar square over 8ma square, nx square plus ny square plus ng square. Okay, so we're pretty much done with three-dimensional box. Then what you want to do is that how the energy level is distributed in such a way, because you have now three quantum numbers. The lowest energy or ground state of this particle in a three-dimensional box is nx equal 1 and y equal 1 and z equal 1, all ones, and then this is it. Okay, then of course your energy is that 8 h bar square over 8ma square times 3. Okay, so actually the unit, I think the unit is that 8ma square over h bar square. Okay, h bar square over 8ma square, so 3. And then second lowest energy level is that 112. So 112, which is 1 plus 1 plus 4. Then that is 6. Okay, and 221 and 311, which is that 9 plus 1 and 1 and 11. And if you have 222, in that case 4 times 4, 4 plus 4 plus 4, 12. Okay, so this is the way you can see the kind of energy levels of this three-dimensional box. Okay, so we have solved firstly one dimension, the particle in a box in one dimension and particle in a box in three dimension. Okay, and I am going to talk about briefly two kind of application of particle in the box. Well, there are other kinds of simple application. Actually, there are many. For example, is the UV spectroscopy, and they handle or they consider the conjugated polyene or cyclic conjugated polyene as a kind of one-dimensional or two-dimensional box, and then they could calculate the energy level and then match to the spectrum, UV spectrum or visible spectrum, and then figure out kind of their behavior like that. So this is very simple application, and not that one, but we are going to solve a little bit challenging tunneling problem or reflection problem. So here you have just space, and your particle travels through the space, but there is a barrier of height v, so energy v, potential barrier, and the kind of thickness of the potential barrier is a, small a. So your potential barrier begins from x equals 0 and x equals a. Oh, okay, this is still one-dimensional problem. So the particle only travels in x direction. Okay, that's fine. Yeah, it just go in one direction. Okay, so your potential negative infinity to 0 is 0. Let's put it 0 or constant, but that's enough. So from a to x, because there is no potential, v equals 0. Or potential is 0. So actual potential of this barrier is v. Okay, so there is a potential height v set up from 0 to a. So your particle travels from minus infinity and plus positive x direction, like that. So it instant from left hand side of x equal a barrier or height v. Okay, so classically, if the energy is lower than v, less than v, it just hit the barrier and then go back 100%. Okay, nothing can go through. But in quantum mechanics, you can go, I mean, that particle may go through even though the energy is less than v to the other side, or to the potential barrier. Okay, so it goes through, but some goes through, some goes back by reflection. Okay, so in this region, your wave function, because potential v equals 0, not this v, but the potential function is 0. This is your Schrödinger equation. You remember the form of the Schrödinger equation for the one dimensional particle in a box? Yeah, this is exactly that, with v equals 0. Yeah, and then the wave function in this region, left hand side, that stands for phi L, is going through and being reflected. So positive plus ikx is going through, minus ikx going back. So getting into the barrier is proportional to a square. Getting reflected is proportional to b square, right? And also the energy term is associated in this way. K square is 2me over h bar square. This is just the same as what you had in solving the Schrödinger equation for particle in a box in one dimension. Okay, and now in the barrier, well, actually energy is not necessarily less than v, but in this case we assume that that's less than that. So anyhow, so there is a potential v, and this is the regular Schrödinger equation for the particle in, not in the box but in the barrier. Yeah, it's not necessarily be the box, but anyhow, this is the barrier. Well, boxes also have something as infinity barrier. Okay, but this is not the box, but it's a barrier. Okay, then your solution, because k is assumed to be this is k square is greater than 0, is put in this way. Then positive k is going through, negative k is reflecting back. Okay, maybe over here. Anyway, okay, so this is the solution. And then in this side you have only one direction. So of course the Schrödinger equation, the form is the same. And then you have only r is the right hand side. Okay, so the coefficient is f e to the positive ikx, and k is the same as this, as the just regular. Okay, and then we are going to study the probability of tunneling, or tunneling probability pt, well, which is something must be here that is tunneled out. Okay, which is proportional to f square, and something must go into the tunnel or the barrier, which is here a square. So tunneling probability is f over a, and absolute value square. That is tunneling probability. Okay. And also the wave function here, there, and there. These wave functions, phi L, phi M, the middle, and phi R, right hand side, left hand side, middle, right hand side, all must be continuous. Meaning is that at x equal a, x equal 0, their value must be the same. That is the kind of boundary condition. In this case, I would say continuity condition. And also their derivative, first derivative at least, must be continuous. Okay, with those continuous or continuity condition met, you solve this problem. Meaning is that you determine A, B, C, D, F. Okay, yeah, E we used it for energy. Okay, so this coefficient, then what you can do is that you can compute the tunneling probability. Okay, so you have done it. Well, this is rather tedious, kind of challenging, a little bit challenging if you have not done yet, and then please just try. And so you try it, and then you obtain the value of A and value of F. Then you do this actually absolute value square of those two, ratio of the two, and you obtain PT. And then this is your energy. So energy just the same as EV at the potential, you know, the barrier height 1. This is the same, and twice, 3 times, and 4 times. So at this point, you have just in classically all passed over V. Then it must be, just to follow this, maybe I'll try my pen. It would be something like just like this. Okay, this is classical, but in quantum mechanics that's not the case. I lost my pen. Okay, laser pointer. Okay, in quantum mechanics that's not the point. Even if the energy is less than V, it has certain probability to tunnel into. But interesting thing is that if the energy is higher than V, still there is less probability. See, not here, less probability than 1. Okay, and also after that, the barrier kind of attract the particle, goes through. Okay, so this is the kind of barrier behavior for tunneling. Okay, and there is a kind of serious application for this is that nowadays people reduce the dimension or size of the semiconductor industry. Okay, now they are kind of narrowing the line width of those, and then you should sooner or later bump into this tunneling problem. So this is the way to handle that kind of application. Another thing is that femtosecond spectroscopy. Now you are using 3 femtosecond time with pulse. Okay, pulse, laser pulse, which kind of short pulse, which is the short pulse of kind of 3 femtosecond. Okay, so this is a application for femtosecond transition state spectroscopy. Okay, so people use this in kinetic study or chemical kinetics as such. Yeah, and then what you seen here, what you are doing here is that, or you're observing here is that energy and time are conjugate variable in uncertainty principle. So delta t times delta e equals or greater than h over 2. Okay, that's uncertainty in time and energy. So energy, uncertainty in energy, if the time is this short, energy pulse, the laser pulse is this short, and the energy distribution or uncertainty in energy is h over 2 delta t. Okay, So what is observed here is that your sample hit with this short 3 femtosecond pulse, the energy observed is distributed in a way because there is an energy uncertainty. And what is observed is the vibrational energy while it is hit by 3 femtosecond laser pulse is between vibrational quantum number 14 to 22. So it's a kind of a resultant state is a superposition of the wave packet corresponding to vibrational quantum number 14 to 20. You see that your kind of a harmonic oscillator potential function is 1/2 k x square. So your whatever the maybe 14, 15, 16, 17, 18, 19, 20, 21, 22, like that. The state here are kind of each wave function or wave packet. Those are superimposed. Okay, that's denote the state of this kind of after hit by 3 femtosecond laser. Then the kind of resultant state is represented by superposition of the wave packet from 14 to 22 vibrational state. Okay, this is a snapshot, and this is the wave function. This is the kind of a snapshot of those two 14 to 22 wave function, total wave function, or superposition of that. And then probability is that absolute value square, which is here. And then you can observe this in time in the next slide. I'm not sure if I can do it. Okay, let's just go. Yeah, I'm sorry. I think I have to go back. Okay, so this is the kind of probability which is going back and forth in your potential harmonic potential well. Okay, so this is the end of, well, let's wrap up, and this is the end of particle in a box problem in quantum theory. Thank you.